No.
Oh, no.
My goodness, you guys are candy hogs.
What about my
Travis candy.
If you guys ask for candy, that makes me not want to give it. I'm just saying.
I give $1 for piece of candy. I didn't
Uh-huh.
ask.
Mr. Trainer does have candy bars for sale.
How
For
much?
$1, I think.
I can buy
Ask
20.
Gary Moyer, he buys them every day, so.
Sure.
Anyways, we are going to start with covalent bonds today. It's actually easier because guess what? It doesn't deal with ions. It doesn't deal with the plus and the minus charges. And so everything we had to learn for the ionic and like valence electrons and how that affects the charge that they will form and all that, it doesn't affect covalent bonding whatsoever. All right, so it's actually a little bit easier. So we're gonna pick up, this is slide number 19. We will get another song today, just so you know. Mr. Edmonds.
Is it as good as the love song?
I don't think so. It's decent. And Mr. Edmonds songs are all good, but
That love song, man.
it really gets you, right?
Right here.
The old ticker.
Made my car explode.
Yes. Okay. I'm glad you guys are always awake. You're always a little extra awake, though.
Yeah, we got past first period.
Yeah. All right. So covalent bonds. They form, shockingly, covalent compounds.
No
Way. And so they form, and here's the key, when they share electrons. So we have two types of bonds, ionic and covalent. Ionic exchange, one gives, one takes, perfect partnership. Covalent, they share them, all right? So those are two very big ideas that you definitely have to keep straight. Ionic is the exchange of electrons. Covalent is the sharing. And so sharing is the key. A lot of times people think, oh, sharing is caring. Sure is. If that's the way you want to remember it, go for it. The prefix co, right? Anybody have an idea what does the prefix co mean? C-O. If I say two people are going to cohabitate in an apartment, what do I mean by that?
They're sharing or doing something together.
Perfect. Can't say it better myself. They're sharing or doing something together. So by putting that prefix co in front of habitate, I know that they are going to share that living space or they're going to live there together. So co means sharing or together. And that's exactly what they do with the electrons in a covalent bond. All right, ionic, Brooklyn, you with me? No shenanigans over there. Covalent, or excuse me, ionic was dealing with one of our metals and one of our non-metals. Here's a difference. Covalent is dealing with two non-metals, okay, two non-metals. And so, again, the prefix co means together, joined, shared, all of those ideas. So it's not that the hydrogen is going to give away an electron, and it's not that the other hydrogen is going to take. That would be representing what goes on in an ionic bond. The covalent bond, they're going to kind of put their electrons together, and they're going to both share them. All right, so you can see here with hydrogen, this electron needs one more to make it satisfied. This hydrogen needs one more electron to make it satisfied. So if they just kind of like come together, they can each, like this one is using them right now, this one's using them right now. So like, it's not like they have to like wait their turn or anything, they just kind of get close enough where the electrons are in both of their areas. And so it's kind of like putting in, like maybe you're gonna, like think about it, like if you're gonna get pizza and there's like 4 or 5 of you, you all put in some money into the pot and that pays for the pizza, right? So it's not like, okay, you know, you pay $2, so you get 2 slices, and it's not like you give or take or anything like that. It's like, it becomes the community pot, everybody uses it, everybody takes from it. And so that's kind of what's happening with these covalent bonding situations. So this is just something that you'll see. A line usually represents a bond. So if I put a hydrogen, a line, and a hydrogen, that tells me I have a covalent bond between those hydrogen elements. Notice that this has 2 lines. It doesn't mean equal. What it means is it's actually a double covalent bond because oxygen is sharing 2 each, all right? This oxygen is 2 away, because it has 1, 2, 3, 4, 5, 6, and this oxygen is 1, 2, 3, 4, 5, 6 away. So if they're able to share 2 and 2, then that will satisfy both of them. But they, just sharing 1 isn't going to be enough, because that would still leave them at 7 apiece, and they're still 1 away. So they have to share 2 to make that satisfied. And that's not something that we're gonna necessarily stress. It's just, as you get into chemistry, you will see that, and so I like to kind of point it out. Now, again, you see the sharing of the electrons. Again, you can see that they're sharing 2. This one belongs to this atom, this electron maybe belongs to this one, and it's not that they've given or they've taken, but they're putting them kind of in that communal pot together, and they can both benefit from them. So now, if you just look at this atom, this has 8 electrons, and if you just look at this one, it also has 8, because of those 2 shared electrons. Again, coming together, this one is satisfied with 2, this one is satisfied with 2, and we represent it with the single line connecting them. Notice that we're using hydrogen a lot. Hydrogen is over there with the alkali metals, and the only reason it is because it has that 1 valence electron. We also said that it typically acts as a non-metal, even though it's on the metal side of the periodic table. So these hydrogens are really acting as non-metals, okay? So hydrogen needs 1, chlorine needs 1, so they actually come together. It's not that hydrogen will give its electron away, or chlorine will take 1. They just come together, put it in the communal pot, and they share it together. So this one is now satisfied at 2, this one is now satisfied with 8. And that's covalent bonding. Simple, right? A lot easier than looking at the ions and having to crisscross and blah, right? So with the chemical formulas, we can't predict exactly what's happening, because there are alternate versions of the same element combination. So there's multiple ways that hydrogen and oxygen will come together, multiple ways that nitrogen and oxygen come together. And so it's not something that we're gonna be setting up and predicting like we did with the ionic formulas. All right, so when we wrote those compounds, we could predict it because the valence electrons were predictable, and we could know what ions they were going to form. And then once we knew the ions, we crisscrossed it and gave the opposite number to the opposite element. So that doesn't necessarily happen the same way with covalent bonding. So we don't worry about that right now. It's kind of above our pay grade for an introductory type course. So you'll get into that more in chemistry. So the covalent bonds, simply this is showing they're sharing 1 electron and 1 electron. The reason that we need 2 hydrogens is because hydrogen only has 1 available to share. Oxygen needs a total of 2. So that's why we end up with H2O, right? And so typically it can be very simple, like 1 water molecule, or it can get very, very complex. All right, here is, and this is not a difficult process either. It's the last thing we'll talk about with covalent bonds, and it's naming. It is a little bit more extensive than with our ionic, because we have to pay attention to the subscripts in the formula now, right? And so, the key is that covalent go between 2 nonmetals. So basically, we're just on the periodic table, we're just looking at the columns, those 3 like over here on the right-hand side. Because remember, our noble gases still just sit there on their donkeys and don't do anything, right? So it's just basically valence group 5, 6, and 7 that are our nonmetals. So we're going to name it the exact same way we did ionic compounds. We list the metal, or we list the first element, then we list the second element, drop the ending, and add I. Right, whoops, wrong direction. So we write the name of the first, write the root name or the beginning part of that second, so ox, nit, iodide, okay? And then we add the IDE. You guys are good at this. This is exactly what we did with the ionic compounds. Okay, here's the difference. Oh, did I go too fast? have to pay attention to the subscripts. We could ignore those in like the K2O. We didn't have to say anything about the 2. We just called that potassium oxide. Problem now is that there are multiple versions of elements combining. So nitrogen and oxygen. We have all these different combinations, and that is problematic. N2O, NO, NO2, N2O5, those are all very different compounds. They are very different, so we can't just say nitrogen and oxygen. I wouldn't know which one you're talking about. So we have to pay attention to the subscripts. And here's how. We have to use the Greek prefixes to match the corresponding subscript. So, if it has a subscript of 1, then it's just mono. Sometimes, like carbon monoxide, you will hear that. A lot of times, the mono is not even included. All right, so I will accept either way. If you put it, that's fine. If you don't put it, that's also fine. All right. Now, the rest of them, you have to put them. If it has a subscript of 2, you're going to have to use di. Subscript of 3, tri, 4, tetra, 5, penta, 6, hexa. And these should all sound familiar from like when you do polygons in, did you do them last year in 8th grade? Usually you do, no? So how many sides does a triangle have? 3. Right? How many sides does a stop sign have? 8, which is why we call it an octagon, right? The hepta is kind of weird. Hexa, we don't use a lot. The pentagon is the building in the Capitol that actually has 5 sides, right? Tetra, is like a tetrahedron, a 4-sided object or polygon. So here's where they actually go. Well, not quite yet, I guess. And again, this is not something that I'm going to count off for, like, if you write these. The more you hear them, the more you're around it, the more it just becomes natural. But the O or the A gets dropped if the second element begins with a vowel, like oxide. You're not going to say mono-oxide. Like, what? Like, so you end in an O, so you're not going to put M-O-N-O and then another O for oxide. So you wouldn't have like monoxide or mono-oxide, right? That's just, like, that's hard to say. And you're not gonna, you're gonna usually call this like pent oxide, where you would drop the O of the oxide. And again, you'll see how these look, and you'll kind of just start getting the feel of it. If you put the extra O or the extra A, I'm not gonna count off on it, right? You understand the general rule. It's just like those small little nuances, and that just comes from experience of what looks comfortable and natural to you. And really, right now, nothing does, because you haven't seen these yet. So again, I won't count off for that, but it is kind of conventional and important. And then the idea that the mono itself may or may not even be included. I don't know why for carbon monoxide it's always given. It really could just be carbon oxide. If you list it, then we know there's at least one. But for whatever reason, carbon monoxide, maybe because carbon dioxide is so common too, like they want to just make sure you're not missing the di. I don't know. But again, I'll count it either way, whether you include it or whether you don't. It still means the same thing. I will have this available to you. You're not going to have to memorize that little prefix table. That will be given to you on your test, or you're always allowed to use it on an assignment or something like that. All right, so just be aware. And if I would happen to forget to give it to you, make sure you remind me, because again, it's not something that I mean for you to memorize. I think that's just loading your brain with random stuff that you can easily look up or easily have available. That will always be available. So here's what happens. You take the subscript, which is like the tail. right? We've been saying that all along. Now I'm gonna kind of mess with you a little bit. That subscript, when we name it, has to jump out in front of the element. So this 2 is gonna have to come out in front of our nitrogen. So what does 2 represent? What prefix goes with that? Billy, what do you think? What prefix goes with 2?
Oh, no.
Oh,
D-I.
the di, the di, right? So it's not nitrogen di. We call this di-nitrogen. The subscript jumps in front and becomes the beginning. So like the tail, the way I think of it, the subscript tail that I've been saying all unit jumps in front and kind of like becomes the nose. It becomes what goes at the beginning. Okay, so notice that I did not put on the monoxide. I could have said dinitrogen monoxide, and that would be perfectly legit and correct. Here I just put dinitrogen oxide. Again, if there's one of them, I have oxide. If I didn't have any, then I wouldn't have any oxide listed at all. But the same thing, it's just nitrogen. Name the first element, name the second, drop the ending, add the "ide," and then make sure you account for your subscripts. So the 2 jumped in front and became di. All right, so do you see any subscripts? So they're representing 1. We could put the mons in front of it, so we could put mononitrogen monoxide, or we can just call this nitrogen oxide. Either way, it is representing the same compound. Sometimes it confuses people to have too many different options that are acceptable. Sometimes people like that. It is what it is. Like, don't stress out about it. Either put the mono or don't put it. You're good. Okay. Okay. So Billy already told us that the 2 represents di. So anybody want to try this one? What will the name be for this covalent compound, Veronica?
Nitrogen dioxide.
It is. The tail subscript is going to jump in front and become di. All right, N2O5. So what is the 5? What's the prefix for 5, Gilbert?
It is hepta.
Wait, for 5?
Oh, 5 is.
Good, so 5 is penta, so we know we're gonna have to have a penta with the oxide. And then the 2 is still di, so what do you think, Brookston?
Dinitrogen pentaoxide.
Very good. Notice how this should be penta, but we're dropping the A off the penta. So you don't say pentaoxide, you just say pentoxide. It just kind of flows together better. Again, if you put the A, I'm not counting it wrong. You're getting the basis of what I need you to get. Okay. Good. Okay. We're doing pretty good. Let's look at this little video. This is dogs teaching chemistry, which is pretty cool. Maybe.
Dogs teaching.
Yeah,
Like,
dogs teaching chemistry. So I'm gonna retire and let the dogs have it.
Welcome to Dogs Teaching Chemistry.
Hmm?
Our first lesson is chemical bonding.
Yep. Dog.
Chemical bonds are what holds atoms together. A chemical bond is an attraction between atoms that allows the formation of a chemical substance. The electrons that participate in a chemical bond are called valence electrons. These are electrons that are found in an atom's outermost shell. Let's take a look at the types of chemical bonds that can be formed between atoms. An ionic bond is formed when one of the atoms will lose its electron to the other atom. This results in a positively charged ion, called a cation, and a negatively charged ion, called an anion. attract, and the result is an ionic bond. Covalent chemical bonds involve the sharing of a pair of valence electrons by two atoms. There is also what is called polar covalent bonds. These are covalent bonds in which the sharing of the electron pair is unequal. The result is a bond where the electron pair is displaced toward the more electronegative atom.
Don't worry about unequal sharing, just realize it's sharing.
Thanks for watching, and we'll see you guys next time.
I think it was just roll something.
Well, actually, we're gonna end with that one. Let's go, so in Google Classroom, today's information has these links, same chemistry site that we've been using. So you don't need to get your computers out, but you might wanna keep that prefix chart out. Di-tri.
Barry, is that green paper due today in English? I hope not, 'cause I didn't do it.
Okay, same general concept that we've been, on this site that we've been looking at. You are going to match the covalent compound name on the left with the correct formula on the right. Notice, there's an NO, there's an NO, there's a CO, there's another CO. There are a lot of repeats, so you have to make sure you're looking at the correct, representation of those subscripts with the correct prefix. Who wants to start? Andy, go for
Nitrogen dioxide is N2O.
it. Okay. N2O. Oh, wait, what did you say?
That's wrong.
Oh, okay. Hold on, let me reset it. So remember so if you're looking at the name, like the name is given, that die is the nose, it has to drop back and become the tail in the formula. So what would it really be? If there's a prefix with it, it's coming, that's what a prefix is, it comes before the word. So really this die goes with the oxygen, and so it's gonna be represented with your subscript behind. So instead of N2O, what is it?
NO2.
It is NO2. Nice. NO2. Where is it?
Up.
Thank you. Oh, I'm struggling. Okay, Andy, you pick. Sulfur dioxide and SO2.
Iodine, heptafluoride, IF6.
Sheesh. That is a mouthful.
Nitrogen tetroxide,
Yep,
did you say, is N2O4.
N2O4. Good. So again, the prefix comes before and it drops down and becomes the subscript behind. The tetra 4 drops down and becomes the subscript 4 behind. Good, you pick.
Sulfur trioxide is SO3.
SO3. Good.
Garrett.
Oh.
Nice.
Garrett is so happy right now. Alright, why don't you try to find the match for CO?
Dang, I was gonna do that. Yeah, so is I.
So what does the C stand for? Okay, so we have carbon, so I have a carbon monoxide, I have a carbon tetrafluoride, and then I have another carbon down here. So, what?
I'm gonna go with the carbon monoxide.
I think that would probably be a really good bet. Now, could I have said monocarbon monoxide? Yeah. But you usually don't see that. But either way is correct, yes. Layla, you have a question? Oh, okay. Let everybody go first, or go once first. Garrett, you pick.
NO is nitrogen monoxide.
Okay.
Down. Third from the
Why, oh man, why is it hard to find?
Is there more down? You scroll down.
SF6 is sulfur hexachloride.
You think sound so smart when you say these.
I'm gonna do iodine, trifluoride is IF3.
Good. You pick, Dave.
Oh. Brooke.
Dinitrogen pentoxide is N2O5.
You pick.
Carbon trait fluoride is CF4.
Nice. So, confidence too, I love it. Echo, you pick.
Egypt.
She's not happy with you now.
Come on, Shorty.
Alright, what you got? What do you think, Egypt? What looks good to you? So why don't you do the CO2 one? What's the C represent? You have disulfur, you have dinitrogen, carbon, and you have a dinitrogen again.
Miss Tobin, we can't
Oh,
see
you
that.
can't see that one? I'm sorry, Dave, you didn't even ask that. On mine, I'm sorry. Sheesh, Louise. I am sabotaging you.
Yeah, you are.
I'm sorry, you didn't even asked that.
Carbon
Sorry.
dioxide.
There you go. All right, Egypt, you get to pick. Return the favor.
N2O3 is dinitrogen trioxide.
Good.
Kanan.
S2O is disulfur monoxide.
And dinitrogen monoxide.
I'm
Awesome.
gonna get your hand
I'll definitely go for those.
All right, let's look at,
Hey, Miss Tobin,
yeah.
your phone's still
Hey,
going.
what?
You got that song.
Thank you.
Did you forget about it?
Yes.
Yeah, what about our phone?